Video we're going to explain a bit about the geometry of the complex exponential map. Okay, so that we'll see in a later video that the complex exponential map is a covering map. It's actually a kind of key example in the whole theory of covering spaces. But this video a little bit is kind of a warm-up for that. So here you should think of this picture here as a strip in the complex plane, and it's oriented with the real axis. So this is the real axis here, running from back to front. And so the complex axis is pointing from left to right. And we've got a kind of finite strip. The back edge of this is where the real part of z is equal to a, and the front edge is the line where the real part of z is equal to b for some constant b that's bigger than a. And then these red lines, so this middle red line is just on the real axis, and then the other ones are all kind of spaced out by 2 pi I. So this is where the imaginary part is 0, this is where the imaginary part is 2 pi or 4 pi or minus 2 pi or minus 4 pi. And so we take some point z lying in this strip and we take e to the z. So it's not hard to see that e to the z is going to lie in this set that we call A here. The absolute value of e to the z is just e to the real part of z, so that's going to lie between e to the a and e to the b. And the geometry of how it works, you see with this, you get this kind of infinite strip. Of course, we've only shown a finite section of it, but in principle, it's an infinite strip, and it all gets kind of curled around and around like that into a helix, and then the helix gets collapsed down to give us this annulus. And all the different red lines, they all get collapsed together. The first one is kind of like everything on the foot. You've got the middle line, which is just kind of the real axis, and then this is stuff that's just real number plus 2 pi I, but when you take e to the 2 pi I is equal to 1, so that doesn't make a difference. This exponentials of the points on this red line are the same as the exponentials of the points on this line and this line and this line, so this all just gets collapsed down onto this this line here in the annulus. So what we're seeing is that the exponential map gives a surjective map from this vertical band B, given by the real part of z between a and b, onto this annulus A, where the absolute value of z lies between e to the a and e to the b. And so every point in the annulus has infinitely many different corresponding pre-images in the band B, and they're all kind of spaced out by multiples of 2 pi I.